Hello everyone, I am Tanvi Joyce and this is my project Seeing Through the Gaps Detecting Climate Accountability Blind Spots in Australasia. Greenhouse gases such as carbon dioxide, methane, nitrous oxide, and nitrogen dioxide trap heat in the atmosphere with long term effects on the environment. This contributes to global warming, sea level rise, ocean acidification, extreme weather events, biodiversity loss, and various other problems. Australasia region is affected by bushfires, droughts, rainfall pattern changes, etc. Accurate greenhouse gases monitoring is very essential to meet the international climate goals and achieve net zero pledges in sustainable development. Effective monitoring of such gas emissions is therefore vital for assessing environmental impact and tracking progress towards the international climate goals and net zero commitments. Here are a few statistics. Compared to 1750, in 2023, carbon dioxide emissions increased by 51%, methane increased by 162%, and nitrous oxide increased by 23%. The major contributor is the electricity and heat, the industries, and the agriculture, according to a study in 2019. A study in 2022 established that the major contributor of greenhouse gases is the carbon dioxide with 71.6%, followed by the methane and the nitrous oxide. Current reporting of these greenhouse gases is from the bottom up approach, which are from the industries, etc. These methods miss big emission leaks and transient events like bushfires. Satellites such as the CAMS and the OMI provide independent measurements for the atmospheric point of view called the top down measurements. There are instances where the bottom up emissions from the inventory suggest progress towards climate targets, but the top down satellite data shows significant gaps beyond statistical uncertainty. This project aims to develop an uncertainty framework which, instead of dismissing gaps between top down and bottom up data as statistical noise, classifies it as climate accountability blind spots. The objective of the study is to deliver a reproducible tool that reconciles the reported emissions with atmospheric reality and such that both the scientists and the policymakers can distinguish between variations and reporting failures. Furthermore, by comparing top down satellite data and bottom up inventory data, the project moves beyond detection of blind spot to explanation. Blind spots can be linked to human activity patterns and major catastrophes. This creates policy ready insights, enabling governments in Australasia to strengthen their defense towards the net zero pledges. Why these gases? The carbon dioxide is the primary greenhouse gas. It accounts for approximately 75% of greenhouse gas emissions and is a major industrial activity indicator. It is long lived in the atmosphere for up to a century. The methane is short term greenhouse gas but causes intense global warming and is sensitive to agriculture, waste, fossil fuels, etc. The nitrous oxide is a long lived greenhouse gas with ozone depleting abilities. It is mainly obtained due to agriculture and soil emissions. And the nitrogen dioxide is a short lived air pollutant which is a tracer for industrial and human activity. It also acts as proxy for the fossil fuel uses and has a strong seasonal variability which makes blind spot detection easy. My contributions to this project are I collected the data sets for multiple greenhouse gases. For the top down approach, I collected it from CAMS for the methane, carbon dioxide, and the nitrous oxide, and from OMI for the nitrogen dioxide. For bottom up, I collected it from the EDGAR database for all the four gases. I did the data cleaning as well. I standardized all the data sets to a common spatial resolution and monthly temporal scales. I handled missing values, unit conversions like converting from flux to concentrations, and variable renaming to ensure interoperability. I did the exploratory data analysis and generated spatial emission maps and temporal trends plots for each gas, and I conducted cross gas comparison analysis. As we progress into the modeling and data integration stage, depending on the top down and bottom up data consistency, other databases might also be used. Model architecture. The data is first collected from both top down and bottom up approaches and then is subjected to standardization and pre processing. Then the exploratory data analysis is done, and then we move on to the data integration stage. Data integration stage comes handy when we want to do comparative analysis for gas quantification. And then we move on to the modeling and the analysis stage. Bayesian spatial temporal modeling gives us probabilistic distributions. We're going to use that, and then we're going to use the bootstrap resampling for stability. Machine learning models like XGBoost, LightGBM are used for downscaling into one into one dimensional grids, and evaluation metrics like R square, RMSE, they are used to validate the same. Then we'll have our uncertainty detection framework. Here are a few visualizations from the top-down atmospheric data that was collected through the CAMS satellite and the OMI satellite, which is the ozone monitoring system. These maps will be standardized to match each other during the integration stage. We can see that the nitrogen dioxide is finer while the nitrous oxide looks a bit pixelated, so all that will get standardized during the integration part. This is a beautiful visualization of the bottom-up data set, which is the EDGAR data set. We have all the three gases, but the nitrogen dioxide inventory is yet to be processed to obtain an image. However, it is collected through the EDGAR database itself. The data was analyzed for average, maximum, minimum, and missing values. There were no missing values found. The variables were renamed to match across data sets, and the data was subsetted to the Australasia region by specifying the latitude and longitude coordinates. Extracted monthly means for instantaneous or annual data to make it computationally easier to work with. And this is a summary table. Here's a small snippet of the exploratory data analysis of the bottom-up data. The carbon dioxide distribution shows multiple peaks indicating strong spatial variability across Australasia. The smaller peaks on the left represent the background and rural regions with low emission intensity, while the larger peaks near the center are dense industrial corridors, power generation hubs, urban zones, etc. The methane histogram is distinctly bimodal, reflecting two major emission regimes. The lower peak corresponds to widespread natural background emissions from wetlands and soil respiration, whereas the higher peak captures concentrated anthropogenic sources from livestock, agriculture, coal, gas, etc. The nitrous oxide distribution is heavily right skewed, showing that most regions emit little, but small agricultural spots emit more. The initial strong peak shows the low soil emissions, and the smaller peaks show the fertilizer and livestock emissions, which are usually related to the nitrogen fluxes in farming regions. Here are two beautiful plots. Both the plots illustrate the normalized yearly emission behavior of carbon dioxide, methane, and nitrous oxide across Australasia from 2015 to 2025. The first one is a trend analysis, and the second one is a heat map. Carbon dioxide rises steadily over the decade with minimal fluctuation, while methane, on the other hand, and the nitrous oxide vary more sharply year to year. This difference occurs because carbon dioxide originates mainly from continuous fossil fuel and industrial activity and accumulates in the atmosphere over time, whereas the methane and the nitrous oxide are strongly influenced by agricultural cycles, climatic variability, and episodic emission events. The visible peaks around 2019 and 20 likely coincide with the Black Summer bushfires, which caused widespread combustion related carbon dioxide releases, followed by short term dips during COVID 19 lockdowns that temporarily reduced the industrial and transport emissions. In conclusion, these early findings demonstrate that the framework is already capturing meaningful emission dynamics across Australasia. This confirms that the data cleaning, normalization, and integration processes are functioning as intended, laying the foundation for the next phase of uncertainty aware modeling. As the project progresses, the focus will shift toward reconciling top down data and bottom up data sets. Quantifying regional blind spots, flagging them, and refining the multi gas comparison framework will be of focus. Here's a small timeline to show where we are at the project right now and the deadline of the project. Thank you.